Okay, everyone, this is a continuation of the lecture for the Laplace domain solution of the radial flow equation. And now we're going to solve it. We're going to invert it into the real domain. And what I was asking a moment ago is when did the bounded circular reservoir solution first show up in the literature as something that basically resembles this? Anyone? It was 1950, the Horner paper. And remember, the Horner paper was not, Horner didn't actually do the work. The team at Shell in the Netherlands did the work, and he wrote the paper. But this equation, or a variant, a slightly different variant of it, showed up in that paper. And they made a very interesting comment. They said that it was not even a solution of the differential equation. It was not even a solution. And for years that bothered me until I re-derived this. But what does that mean, Eric? This is not even, it looks like a solution of differential equation, but what does it mean? Class? If you plug it back into the differential equation, you have some nuts and bolts left over, right? So whenever you work on something and you have some nuts and bolts left over, it's probably an approximation. Hopefully it's a good approximation. When you do the transient solution and you substitute that back into the differential equation, you actually have something that is like 1 over t, so the equals 0. So the larger the time is, the more accurate it becomes, which is fine. I told you this story about my neighbor who had his car completely taken apart by the guy who had a plate in his head, and he had a bucket of bolts and stuff left over. I mean, that's what happens when you do this. Now, I'm going to tell you that when we solve this particular case, this is not something that you would just get the first try. Fortunately, you know, people like me have been through it, and others, and there's a specific strategy of how you take things in and out of this solution to get here. I will tell you that I had an extraordinarily bright young student from Taiwan who actually carried this to a few more terms. And unfortunately, what happened is those higher order terms actually caused this solution to fail. Okay? So if you're thinking that when we start doing these asymptotic expansions, that if I carry a few more terms, it'll just get more accurate, wrong. It didn't happen for this case. So instead of, I think we used a 2-term expansion, he used a 3, it actually started deviating. And it's probably because there's a multiplication of the 2, and that amplifies it. But suffice it to say, we'll derive this in a moment. Now, the first thing we're going to derive is going to be the infinite acting solution, which is kind of trivial. We've already done that last night. And then again, we'll also do the so-called logarithmic approximation. Okay. So here we go. This is all from the previous work that we just completed. So this is a summary of equations. And again, just so everybody's familiar, cylindrical source solution, infinite acting reservoir, line source solution, infinite acting reservoir, log approximation, infinite acting reservoir, no flow outer boundary case, infinite acting reservoir, which we just derived. And for the case where U is approximately approaching 0, we get this, which is what we just derived. And of course, the constant pressure cases are down here. So coming back and talking a little bit about, you know, what we're going to try to do here. Suffice it to say, this can be solved directly using the Moulin inversion integral, but it's really ugly. So there's a couple of variations of this, and as Mr. Ravi Kumar mentioned, this was 1949, Van Everdingen and Hurst. They solved this using the integral, the Moulin inversion integral, and they ended up, instead of having I's and K's, they ended up with J's and Y's. And, you know, I have no idea how you would have calculated this in 1949, but that's okay. So we'll start with the line source solution, which is given here. And then we'll go ahead and multiply through, take a couple of things, and, you know, we'll manipulate and so on. What we really need to do is we need to know what is it we're trying to invert. So we're going to try to invert the K0 square root of U RD. And when we do that, the question is, what is that going to look like? So we have K0 square root of U RD. And when we take the inverse Laplace transform of that in the book that I've given you, Bromwich and Stegen or Robertson Kaufman, you get this, which is 1 over 2t exp minus a squared over 4t. Do you recognize 1 over 2t exp minus a squared over 4t, class? Yes. We derived this last night using the Boltzmann transform. And then we have to integrate this, and when we do, we end up with a line source solution. However, if we go back to the original form, which is here, this is the original form. So this is actually the derivative of the form we want, or at least it's the derivative in real domain. It's the value multiplied by u in the Laplace domain. It's actually 1 over u K0 square root of u times a. From Karslov and Jaeger, that's 1/2 E1a squared over 4t. So that is trivial, but it's the only place I ever found it was in Karslov and Jaeger. So the final result, however you want to represent it, is given here. That's your dimensionless pressure solution, just like we got last night. And then the derivative solution is here. So it's this expression. Okay. Mr. Ravi Kumar, let's take this solution and multiply it by TD. So that's TD multiplied by that derivative. What happens to that TD? It cancels, right? So we have 1/2 EXB minus RD squared over 4TD. Would you believe me if I told you that in 1980 someone proposed that as an analysis equation? Remember, everybody and their brother has taken credit for the derivation of the pressure derivative, right? I've had at least 2 people in short courses who work for Schlumberger take credit for it. Bourdais taken credit for it. Anil Kumar and Djaber Tiop's taken credit for it. Probably someone else has taken credit for it. When did the pressure derivative, as we know it, actually show up in the literature? Anybody? 1980. Okay, it's a good guess. Anybody else? Mr. Bake? In order to get through some of these derivations, we had actually derived it years ago. But the first time that it ever showed up in the literature apparently was in the 20s, along with the Tice solution, and it was called the Chow derivative group. I don't know who Mr. Chow was, but Raghavan prefers to reference him instead of all of these other guys that came along in the petroleum industry in the 80s. Just FYI. So, here we go again, people taking credit. And that's great. I mean, it's good that the derivative came along because it really changed everything. But how would you feel about equation, 16 as an analysis equation? What does it say? It says that the pressure derivative is a decaying exponential. Is this a plausible solution, class? Let RD be 1. Let RD be 1. Mr. Bake, minus 1 over 4 TD. TD is very close to 0. What happens? That's negative infinity. What's the argument of e to the negative infinity? 0. There's no way this is going to work, is it? But it's a very clever little paper that somebody wrote on this. I mean, look, people were trying to figure out how to do what? How to estimate permeability, which is in the PD definition, from either pressure or pressure derivative. Okay. They just got ahead of themselves. All right, so that's the easy one. And then the next one, and again, I didn't point this out, but the well testing derivative is TD multiplied by the derivative PD, and that's the derivative we use everywhere. The next is to talk about the logarithmic solution, And again, as I mentioned, we're going ahead and separate it term by term. And when we do that, the minus 1 over log u, or sorry, minus 1 over u log u, what is the inversion of that? Well, it turns out that it's a natural log of t plus gamma, or natural log of e to the gamma. And gamma is, math ladies, 0.577216 ... Euler's constant, right? And that's given in Abramowitz and Stegen and Roberts and Kaufman. Okay. And then, of course, this is just the integral of a constant. So, or sorry, the inverse Laplace transform of a constant. So our final result is 1/2 natural log e to the gamma td, and then we have natural log of 4 over e to the 2 gamma, 1 over rd squared. We marry these two together, and we get this e to the gamma cancels with that e to the gamma, so we have natural log 4 over e to the gamma td over rd squared. Okay, so that's our so-called logarithmic approximation. What happens when you take the derivative of this form, class? Well, let's separate it into these terms. What's the derivative of a constant? 0. Okay, so here's where things get interesting. When you take the derivative here and multiply it through by time, the derivative of a natural log is 1 over t, or 1 over x, whatever it is. We have 1/2 multiplied by that, and then, of course, this whole thing goes to 0. So the derivative of this expression is 1/2. Okay. And that's pretty much where we're at. So that thing that I was telling you before that the gentleman tried to do in 1980, he was trying to analyze very early time derivative data, and of course the equation that we showed you just a moment ago is not going to work, because at 0 this thing is going to be 0. So this TD needs to get fairly large. It needs to overpower the 1 if it were at the well bore, and in that case we would have to be at a fairly large time, maybe TD of 100 or something like that, maybe TD of 25, something like that, where this argument, instead of going to 0, goes to 1, and when it does that, they'll be exactly the same, obviously. Okay, so now we are at the point of no return. Now we're going to try to invert equation 5, which is the boundary dominated flow or pseudo-steady state or bounded circular reservoir system, whichever one you want to call it. The very first term is trivial, right? Because we've already done that. What is the inverse Laplace transform of that, class? It's 1/2 E1 RD squared over 4TD, or sorry, it's 4TD over RD squared. No, it's RD squared over 4TD. Sorry, my mistake. Okay, so the first term is trivial. It's just the infinite acting term. I guess if I'd have looked down there, I would have seen it. So now we're going to focus all of our attention on the inverse Laplace transform of 1 over u k1 square root of u RED divided by I1 square root of u RED multiplied by I0 square root of u RD, not RED, pardon me. Now, it would be nice if K1 and I1 did something like what? Just behaved, right? Because they're at a very large argument of RED. RED is going to be a big number. And you might hope that something interesting happens, but unfortunately, hope is not a battle plan, as they say. So what we're going to do is we're going to look at the behavior of K1 and I1, and then of course we're going to have to come back and look at the behavior of I0. So somehow we're going to come up with an algebraic expression where we take the I1 and K1 quotient and multiply it by I0, and we're somehow going to come up with an algebraic expression that actually makes sense here. It's not going to be pleasant, because the answer is the path we're going to follow, but getting to that path was not simple. I mean, this looks like I did it in one pass, but I didn't. So the first thing we'll do is we'll look at the recurrence relations, where we have the recurrence relations between I and K, and then so we're looking at the relationship between I0 K1, I1 K0, and that gives us that expression. Now, some of you will point out that I did not have to use the recurrence relations to do this, but I'm actually wanting to end up with a relationship in terms of k's, so we're going to give that a try. Okay, so 25 will probably be one of our expressions. And of course our case is n equals 1 as well, so we may end up using that. We'll do some algebraic manipulation, and it turns out that k1 is equal to this mess, which is kind of getting close to what we were trying to do, but not exactly. So we'll have to come back and look at some more of that. And then we look at the recursion relationships for I, and we end up with these expressions, and we finally solve this. And then we have, of course, the expression for k1. So again, I probably didn't have to do all this work, but I did. So k1 is equal to z over 2 k2 minus k0. Again, all that work from whatever it was, 25 to 29, was to do that. So what I've done is I've exchanged that term that was over here for k1, I've exchanged it for a difference between k2 and k0. And I realize some of you are thinking I must have rocks in my head, but there is a bit of magic here that's going to happen in just a second. What we're going to do next is we're going to have an expansion for I0 and I1, and we're going to go ahead and take a two-term expansion, or actually it's a one-term expansion for I0, and we'll take a two-term expansion, but it's actually a sort of a one-term expansion for I1. But I guess you could say they're both two-term expansions. And again, if you carried these out further, you would have more terms, but I'm thinking that it's probably not going to end up the way you want. So I0 of B divided by I1 of A, which is our form, is 2 over A, 1 plus B squared over 4 plus, or divided by, 1 plus A squared over 8. And if we assume that this is really small, then we can express this as a binomial series. Binomial series is given as this. If we do that, and I'll just cut to the chase, we can expand this, and we finally end up with something that looks like that. And again, you could carry it out more terms, but I don't think you'd be very happy with that. So substituting back this equation 37 into equation 30, so this expression here is going to go here, then we're going to have this 2 over A1 is going to cancel with this one, and then we're going to have here, and finally we're going to end up with an expression that's 1 over u k2 square root of u red minus k0 square root of u red, and then minus, or multiplied by, 1 minus this u red squared over 8, u rd squared over 4, and we're going to just go ahead and do this out term by term. So algebraically, we have the infinite acting term, we have the k2 term, we have the k0 term, we have the k2 term multiplied by this, and we have the k0 term multiplied by that. Is this invertible, class? Yes, because term by term, the whole point of this was to expand it term by term, and doing that, we have 1 over u k2, 1 over u k0, we have nothing k2, nothing k0. What's going to happen here, class? Well, we have to go to the book, and we have to figure out what's what. k0 inverts into this, we already knew that. 1 over u k2 inverts to this, and then k2 inverts to this. And so we substitute all of those in, and what happens is we end up finally with an algebraic expression down here given by equation 41. But does anyone have an issue? I'll go back through this really quick. This is the infinite acting solution. This is the derivative of the infinite acting solution, which you've already looked at. This is the K2 solution, and this is the derivative of the K2 solution, if you want to think about it that way. So the final answer looks something like equation 41. If we split equation 41 out term by term, that's the infinite acting term, this is the material balance term, and this is the leftover term, which arguably I called it the shape term, but it would probably be the transition term. This is the early time term, this is the late time term, and this is the thing that makes them connect. Okay, so this was really clever, and I know you're all saying, who cares, it's for a bounded circular reservoir, but imagine that you could do something similar to this for any particular case where you're having to do an expansion. Now, I strongly suggest you go through and do the algebra on this. You know, don't just copy it, but think about it. Think about, would you have another strategy on how you would do those expansions? I realize the previous page had a lot of what appeared to be hand waving, but the goal was to reduce to an expression, and again, I didn't have to go through all the recursion relations, but deriving it this way shows you how to do it, that expresses K1 in terms of K2 and K0, and then the other, really the magic of this whole thing is here, is equation 37. They did not give any guidance on this solution in the Horner paper. So, you know, again, I had to kind of reconstruct it. And what's the value of this solution, class? Anybody? Is there anything you can think of that would be, so you can demonstrate the behavior of the infinite acting portion, you can demonstrate the behavior of the finite acting portion, and you can demonstrate the behavior of the transition term. Could you use this for something else? Is there any practical use of this equation? Yeah, you could, except decline curve analysis, we need, instead of this expression, we're going to have to express it as constant pressure case. I got some news for you. The constant pressure case is going to be the reciprocal of that. And that ain't going to fly, is it? I need you to think about that. That's not going to work, is it? Can you take the reciprocal of equation 40 and invert that? It's a little more complicated than that. We'll derive the convolution and on Friday. Right, but the algebra is still going to end up with the same form. That's one of the reasons we always work on the constant rate solution. But you're correct that we're very, very close. That if we could figure out, I mean, well, let's be honest, that is not going to convert into anything meaningful for the constant pressure case. It's a great idea. I wish it worked, but it's not going to work. The reciprocal of K0 is not going to invert. The reciprocal of that whole mess is not going to invert. What do you want for Christmas, Mr. Ravi Kumar? I was kind of hoping you'd say the inversion of equation 40. Okay, we'll see what we can do. That is all I plan to do tonight. Just so everybody knows, you know, I'm happy to stop here. Could you use equation 42 as a superposition formula? Yeah, you could. It might even be cleaner in some regards. But the unnice thing about equation 42 is it doesn't really die off. So I'm not exactly precisely sure what would happen using equation 42 as a superposition formula, but it might work. I'm just staring at it. I'm not sure it would do what I want it to do. But this is an approximate complete solution. What happens if you insert equation 42 back into the original differential equation? Cam? Do all terms cancel? No. Why? Because we made approximations along the way. The definition of the Bessel functions K2 as a function of K0 and K1 is not an approximation, but what we did to I0 and I1 is, and it is not going to reduce. Okay. Now I'll tell you, for graduate class, we derived this. For undergraduate class, I give them this and tell them to substitute it in a differential equation. And I know it looks ugly, but you know, it's a 10-minute exercise to derive this out and see everything cancel or not. Okay. So what's tomorrow night? Fractured wells. Okay. Now we derived tonight the solution for a single line. What are we going to do tomorrow night? We're going to integrate that line from minus XF to plus XF, so over 2XF. When you integrate a line that direction, what do you get? You get a plane. There's our fractured well solution. Okay. So the original fractured well solution was derived in 1973-74 by Gringarten, Ramey, and Raghavan, right? Except that it also showed up in the heat conductivity literature in the late 50s. Just trying to remind you guys, everything that's been done has been probably done by somebody else. Okay. Now, what is the assumption of this line? How does fluid come into that line? Uniformly, correct? At all points, the influx is uniform. So if I integrate that line across a plane and create a plane, that is a uniform flux plane, correct? What do we use in petroleum engineering? Do we use a uniform flux plane? No, we use an infinite conductivity plane. So tomorrow night when we talk about this, what is the pressure drop from the tip of the fracture to the wellbore? Well, uniform flux says it's non-zero. Infinite conductivity says it is zero. There's also a finite conductivity case, correct? The finite conductivity case implies that the fracture has thickness and it has permeability. So there's actually a pressure drop down the fracture due to flow obstruction being whatever is the conductive material. That was derived in 76, 77 by Cinco and Samaniego. Okay. Again, all this seems trivial because now you have it where you just push a button on the computer. But back when we were working on creating these type curves for RTA, it would take overnight to run the fractured well solution. That's how difficult the Cinco and Samaniego or Cinco and Ming, which was a Laplace transform version of it, was. Why? Because if you have a finite conductivity fracture, what do you have to do? How many of you are taking Dr. Moridi's class? Higher? Okay. What do you have to do? You have an analytic solution on the outside in the reservoir. What are you going to have to do to the fracture if it has finite conductivity? You have to discretize it. Why? Because you have to solve for the flux and the pressure at the same time. Now, I will tell you that Bobby Poe, who sat in that building across the street with me as a graduate student, derived an analytic solution to this problem. Where is it? Schlumberger will not release it. It's in a patent. It's a direct solution to this problem, but they will not release it. Okay. Why won't they release it, Cam? Because they're bad people. They went through a phase where they were patenting everything. Because why? Because Halliburton had a division, they had a division. One would invent something, the other would invent something, and they'd patent it. Who's the loser? We are. I mean, I'd like to see that solution to understand how it works. It is a really, really unpleasant solution. I think Bobby told me it took him 70 pages. That's 70 pages by hand to derive it. But it does exist. Maybe I'll get him to do a lecture for us in well testing or natural gas engineering class, and maybe he'll share some of his insights with it. Why is it so important to have a direct solution? Fast. So when you see Kappa solution or IHS's solution or somebody else's solution, what are they doing? They're cheating. Why? Because you cannot solve that problem that fast. It takes too long to solve that problem that fast. They must be storing values of it or having some sort of a correlation where they calculate part of it. Just warning you guys, okay? If you don't like that, then use the numerical option. It'll be the full solution. By comparison, the analytic option, you know, when you hit return, it goes across the screen. What happens with the numerical option? Go have dinner, go have a nap, call your mom, you know, maybe it's done by then. So, okay, that's tomorrow night. We'll talk about the fractured wells. And then the following night, on Monday night, we'll talk about naturally fractured reservoirs. And then Friday night, we'll talk about convolution and wellbore storage. And then we're done. And I think in the interest of your sanity, I was given to saying that I'll just distribute the exam as prepared. But what's the general consensus? Do you guys want individual problems, or do you want... I can't do mix and match. So, because then somebody will say, well, I didn't want this. But it either has to be all or nothing. You guys don't want individual problems. You do? Okay, so we'll still continue to talk about it. But at some point, I got to release the exam. But it has to be unanimous. I'd rather release the exam, but that's just me because I'm lazy. We're going to have a couple of lectures on the exam too. Just FYI. We've got to make a decision. You guys really don't want an independent problem, do you? I guess we could make it a bonus. That doesn't really help because you have to do the reading portfolio and the homework portfolio anyway. I think we'll just go with as it planned. Unless, one last time tomorrow. So if you have a change of heart, we'll take a hand vote tomorrow. Let's see. But if one... Can you get... I can't do that because then someone would come back later and say, I had a really hard problem. It cost me an A. I want to go back and do the final exam. I mean, I guess I could make you sign a sworn statement or something, but the chances are if you do an independent project or an independent problem, that it will not be, well, I'm not speaking of you personally, but it will not be as much work as the final exam. And that bothers me. I shouldn't have brought this up. I should have just given the final exam out at the start of the semester, which is what I was thinking about doing. But then I thought you'd work on the final exam and not on the homework portfolio, and then, you'd try to skip it, and then something bad would happen. I'm probably delirious right now because I've been here since like 6 o'clock. So this morning. But actually, I got up at 6, but I didn't get here till 7. But that's okay. You should never go to Walmart on a Saturday morning. Just a piece of advice. Went in to get one thing, came out with 400 things. So I need a proctor. I need somebody to go with me. Cam's volunteering. I can see that. Okay. If you guys really want to do an independent project, you guys talk about it amongst yourselves. I'm fine with that. Because the homework portfolio and the reading portfolio is more than enough for me. But I can't... I'm sorry I seem like I'm bipolar here, but the one time I did this where, I allowed people to choose between one or the other, the people who didn't get what they want came back and said, well, I wanted to do the other one. Well, life isn't like that. You have to choose, and it's... I got enough headaches without creating more. And for the distance learning students who aren't here, I'm sure you're going, man, that guy's probably needs to take his medication. I would love for you to do independent problems, but it's going to be more work on your part to equal my expectation for the final exam. How's that? Ravi Kumar had a question today about 6.8 and 6.9, and 6.8 and 6.9 should be solved like 6.7. You understood that? Okay. I realize there might have been some lack of clarity there, but you got it now. Yeah. There's no subliminal message that they're somehow different. They're the same as 6.7. Okay. Last questions? Yvonne, you need to type, I'm not from Bolivia on your forehead, okay? All right, so we'll see everybody tomorrow night, or most everybody tomorrow night. Okay, everybody have a good night. Thank you, everyone.